Hello, I'm Bastian from the Distributed Computing and Systems Group at Chalmers University in Gothenburg, Sweden, and I'm going to present now our paper Ananke, a streaming framework for live forward provenance. This work deals with provenance and data streaming, so let's begin by explaining each of these terms in more detail. Data streaming is about processing unbounded streams of timestamp input data called tuples in a continuous manner. Let's take a simple example with streaming queries receiving an input stream of pictures taken by a car's camera every minute to detect various types of objects. Since streaming datasets are unbounded, input streams are split by queries into sliding windows of a desired size and slide. The first example query counts the number of cars using non-overlapping windows of 1 minute and reports that number if it is greater than 0. The animation shows the detected cars in each image and the output tuple produced from each window. The second query is counting the number of bicycles detected during a window of 2 minutes, with each window having a slide of 1 minute. So like above, the animation illustrates how the outputs are computed. In data streaming queries, it can be quite useful to associate each output with the inputs that led to its creation, for example, for debugging purposes. The state of the art is that such information is provided by fine-grained backward provenance, which can be provided by several streaming frameworks, where each output is associated with all inputs that led to its generation. Notice that due to overlapping windows, backward provenance streams include duplicate provenance data, such as images 1, 2, and 3 in the backward provenance stream you see here. In this work, we aim to transform such backward provenance streams into a single stream of what we call live forward provenance. Specifically, this allows to immediately detect all outputs that depend on a specific input, solves the duplication problem, and gives live information on whether any source tuple could still contribute to a result in the future, or whether its provenance is already final. Before we discuss Ananke in detail, we introduce some necessary terminology. The slide shows a simple streaming query composed of a data source, operators, and a sink. Data items in data streaming are in the form of tuples, consisting of the event time of the generation called timestamp, as well as an additional payload. Because streaming analyses can happen in a distributed fashion, tuples do not always come in strict timestamp order. So to ensure correctness, sources and operators generate special messages called watermarks. Receiving a watermark is a promise that no tuple with a timestamp less than the watermark will be seen in the future. Tuples are processed at operators. Stateless operators process one tuple at a time and generate outputs that match the input's timestamp. Stateful operators maintain state, usually in the form of windows of specific size and slide, similarly to the ones we saw in the introductory example. The animation shows how tuples are split into different windows based on the timestamp. When the analysis has progressed such that the window will not receive any more tuples, the window closes and results for that window are produced. The timestamp of these results for stateful operators is equal to the right boundary of that window. We now define the problem of generating a stream of live forward provenance. A group of n queries processes tuples from one or more input streams and generates streams of output tuples. Existing streaming provenance tools produce streams of backward provenance, connecting each output to the inputs that led to its generation. Ananke, our system, aims at transforming such backward provenance stream into a single streaming graph of live forward provenance. This graph, visualized at the bottom left, is a bipartite graph whose vertices are the deduplicated source and sink tuples. An edge exists in the graph between a source and a sink tuple if that source tuple contributed to the generation of the sink tuple. The graph also contains liveness information, shown as ticks in this animation. These ticks, that we call labels, indicate if a tuple has expired and will thus not be connected to more sink or source tuples in the future. We want to generate the live forward provenance graph as an ordered stream of its components, shown on the bottom right. There are 4 types of components in this stream: sink and source vertices, the graph's edges, and labels. Let's now regard the live forward provenance graph plotted over the event time. Since source tuples cannot contribute to a result backwards in time, the sink tuple is always expired the moment it is produced. But what about source tuples? With multiple overlapping windows and tuples belonging to one or multiple queries, it's not obvious when to call them expired, meaning when they will not contribute to change in the graph anymore. So when looking at the exact state of the execution of the query at a point in time, we could actually draw a boundary such that all tuples, even source tuples to the left of it, are expired. Since we measure time by the incrementing of watermarks, the liveness boundary for sync tuples ends just at the latest watermark. We get an expiration boundary for source tuples. For source tuples on the right of the boundary, we cannot know for certain that there will not be a potential future sync tuple connecting to them, so we cannot yet mark them as expired. We call U the distance of the expiration boundary from the current time. We prove that we can statically calculate the value of U from the window sizes along all possible paths a tuple may take in a query. With U, we can decide at what point in time a tuple has expired just by watching the watermark and a tuple's timestamp. We compare two implementations of our Ananke framework, focusing on different performance aspects. The first one is a user-defined monolithic operator called ANK-N. This implementation is optimized for single-thread performance and is based on a fully custom operator. We also provide a second implementation. ANK-N is a composite operator consisting only of common SPE operators. We prove that ANK-N delivers the correct forward provenance graph, just like ANK-N does in our paper. While ANK-N has a more complex implementation, it leverages exclusively native and built-in operators as join, filter, map, and aggregate, allowing it to leverage an SPE's native parallelization capabilities, and thus we get a parallelizable Ananke implementation for free. Let's now turn our attention to the evaluation of Ananke's performance. Ananke is implemented and evaluated on top of Apache Flink. We evaluate Ananke both in low-level devices that could be found at the edge of cyber physical systems, as well as on a high-end server. Now, in the interest of time, we provide some highlights of the evaluation of this presentation, and we invite you to check the paper for much more details. We begin with showing the overhead of Ananke compared to the state-of-the-art in streaming provenance, which is minimal in most experiments. And then we compare the trade-offs between ANK-N and the composite ANK-N. Let's begin with the state-of-the-art. We evaluate queries from the linear row benchmark running on a low-powered old-world computer. The results, shown in the plots, illustrate the query rate, latency, memory, and CPU consumption. The green bar shows the query performance without provenance, the orange bar the performance of the state-of-the-art streaming provenance, and the two blue bars show the performance of ANK-N and ANK-N respectively. The numbers inside Ananke's bars show the percentage difference compared to the state-of-the-art, and as seen in the plot, for these queries, Ananke has a negligible impact on the query performance. The second highlight is Ananke recording live forward provenance for object annotation queries that enrich an in-vehicle computer vision system. The performance of these queries running on a server is shown on the right side. As already evident from the rate of the queries without provenance, these queries are computationally demanding. Ananke causes a minimal drop in the rate of the query compared to the state-of-the-art. While it does lead to a higher relative increase in latency and CPU consumption, both of these are still small in absolute values. Next, we turn our attention to the trade-offs between ANK-N and the composite ANK-N, with a focus on the scalability of the latter. In this experiment, we use synthetic queries so that we can find the maximum throughput sustainable by each technique. The first column shows the performance of ANK-N, and the second the performance of ANK-N for 1, 4, and 8 concurrent queries, shown in the x-axis, and different degrees of parallelism shown as differently colored bars. Since ANK-N is not based on native operators, it cannot be parallelized as transparently by the SPE, and its performance remains unchanged regardless of the parallelism degree of the SPE. On the other hand, ANK-N can be scaled transparently, which is evident by its increased performance when the parallelism increases until it saturates. In general, ANK-N outperforms ANK-N for higher degrees of parallelism. To recap this video, Ananke extends streaming tools for backward provenance and produces a live bipartite graph of forward provenance. This provides rich information about which source tuples contribute to query results and whether these contributions are final. Furthermore, we deliver correctness proofs of our reasoning and implementations in the paper. Our evaluation shows that Ananke incurs small overheads, and we invite you to check out our paper for more evaluations of Ananke, as well as comparisons with alternative implementations. Lastly, feel free to check all the artifacts on our GitHub account. And thanks a lot for watching.